Hello everyone. Today we will be talking about L'Hopital's rule. The formal definition of L'Hopital's rule states that for functions f and g which are differentiable on an open interval a, b containing c, and the limit of the quotient of f of x over g of x approaching c is indeterminate, then the limit of f of x over g of x approaching c is equal to the limit of the derivative of f of x over the derivative of g of x approaching c. Here's the numerical version of the rule. Now, what does L'Hopital's rule do? L'Hopital's rule solves indeterminate limits. Indeterminate limits are where the limit of x approaching c of f of x is 0 over 0, or the limit of f of x where x is approaching c is equal to infinity over infinity of positive and negative of some sort, which means positive infinity over negative infinity over positive infinity, or any sort. L'Hopital's rule describes taking the derivative of the numerator and denominator in a quotient. As shown here, when you enter limit of x approaching c of f of x over g of x into L'Hopital's, you get out limit of x approaching c of f prime of x over g prime of x, which does not change the limit. Some general guidelines for L'Hopital's rule is you may only use it when the limit is in a quotient form, as in f of x over g of x. You can only use L'Hopital's rule when the limit of the quotient is indeterminate, and if L'Hopital's rule has been used and the resulting limit is still indeterminate, you can use it again. Let's do a few sample problems. We have the limit of x approaching 0 of e to the x minus 1 plus x all over x cubed. As always, we need to make sure that this limit is indeterminate. By substituting in 0 for x, we find that we get e to the x, which is now e to the 0, which is 1, minus 1 plus 0 over 0 cubed, which is effectively 0 over 0. Since this is indeterminate, we can use L'Hopital's. Taking the derivative of the numerator, we get limit of x approaching 0 of e to the x. This is a constant, so it turns to 0, plus 1 over 3x squared. Substituting in 0 for this, we get e to the 0, which is 1, plus 1 over 3 times x squared, which is 0, which ultimately turns into 2 over 0. Now, we must remember that it's x approaching 0 and it's not x equals to 0, which means that we can think of it as 2 over an arbitrarily small number, which then we get is infinity. On to the next problem. The limit of x approaching pi over 2 of sine x minus 1 over x minus pi over 2. We must, as always again, prove that the limit of this function approaching this number is indeterminate. Sine of pi over 2 is 1 minus 1 over pi over 2 minus pi over 2, which is equal to 0 over 0, which is once again indeterminate, which means we can use L'Hopital's rule. Taking the derivative of the numerator, we get limit of x approaching pi over 2 is equal to the derivative of the numerator, which is the derivative of sine x, remember, is cosine x minus 1, goes away since it's a constant, over 1. This goes away also because it's a constant. Now we have our new limit, and we can evaluate this limit at x approaching pi over 2. Cosine of pi over 2 is equal to 0. And that is our answer. The limit of this function is 0. Now, on to our last problem. we have the limit of x approaching infinity of x to the 1 over x. Now, to bring down that exponent, we would need to somehow use natural logs. Temporarily setting y equals to the limit of x approaching infinity of x to the 1 over x. We can take the natural log of both sides, getting natural log of y is equal to the limit of x approaching infinity of the natural log of x to the 1 over x. Now with this, through logarithmic laws, we can bring down this power down to the front. So now we have ln of y is equal to 1 over x times the limit of x approaching infinity of ln of x. Now, with limit laws, we can put that 1 over x back in to the limit function. So now we have natural log of y is equal to limit of x approaching infinity of ln x over x. I simply just combined these two functions. And now we have ln of y is equal to this limit. We notice it is a quotient, so now we can put L'Hopital's into rule. We can use L'Hopital's rule into effect. So now we get ln of y is equal to the limit of x approaching infinity of the derivative of ln of x is 1 over x, and the derivative of x is equal to 1. Now we have the natural log of y is equal to the limit of x approaching infinity of 1 over x. And we all know that when you substitute infinity in over 1 over infinity, you get something arbitrarily, not arbitrarily, but you get something very small. So we have 0. Now that we know that the natural log of y, remember how y is this x to the 1 over x, is equal to 0, we can now plug that in into another clever function, which is e to the ln of y. Now remember that e to the ln of something is the same thing as that something. So basically, we just raised this to e to the ln of x to the 1 over x. But now we know the limit of ln of y is equal to 0, which means we can legally substitute 0 into ln of y. So we get e to the 0, which is equal to 1. So our limit is 1. Here are some common errors and tips for L'Hopital's rule. Remember, L'Hopital's rule can only be used to solve indeterminate limits. If the limit you're solving does not turn out to be indeterminate, then you may not use L'Hopital's rule to solve it. Remember that L'Hopital's rule can only be used in quotient form, as in limit of x approaching c of f of x over g of x. If it is not in that form, you would either need to find a way to turn it into that form or try another method. L'Hopital's rule requires the use of taking derivatives. Please take your derivatives correctly. From the chain rule to power rule, you have to know how to take your derivatives correctly in order to effectively use L'Hopital's rule to get the right answer. Another point worth noting is that L'Hopital's rule occasionally fails to give a useful result. For example, in this result, limit of u approaching infinity, the derivative is taken in the numerator and denominator numerous times, and at the end, through simplification, turns back to its original function. Occasionally, L'Hopital's rule will produce something like this, and you will have to use another approach like a table or the squeeze theorem to figure out the limit. That's most of what you need to know for L'Hopital's rule. Thanks for watching.